So this is the last section in um, chapter 22, and we are talking about massive stars. So stars greater than 2 times the mass of our sun, and how we end up with heavier elements in those stars. So let's first talk about some comparisons as far as lifetime. Um, we've talked about this, but I want to really point out that the higher mass a star, the faster it will fuse its fuel. Um, so more massive means a higher pressure inside. High pressure means high temperature. High temperature means faster fusion. And if you're talking about a muscle car, big cars with big engines burn more fuel than smart cars. If you're talking about a bonfire, you can build a tiny little fire and use 2 logs and last all night, or you can build a big fire and burn up half a forest in a couple, an hour or two. So small stars, much shorter, much smaller fuel source, lower temperatures, and therefore longer lifetime. Um, Also, comparing sizes just to really solidify this in your head. Um, you know, Tiny little white dwarf um, would fit inside the core of our main sequence. Low mass star. The entire sun would fit inside the core of a giant star like Aldebaran, and a giant star will fit inside the core of Betelgeuse. Betelgeuse is a big or a super red giant. So just reminding you on the sizes. um Eta Carinae is a really kind of interesting star. um it is a hot supergiant, at least 100 times the size of our sun, one of the most massive stars that we know, and it has these 2 lobes of material that are reminiscent of the planetary nebula that we looked at a minute ago, except that the star is still there. It has not exploded. Um, so this pink material was ejected in an outburst that was viewed in 1843. This is the largest mass loss event that we have ever seen a star survive. So the star is still there. The lobes are moving away from the star at 1,000 kilometers per hour, very rich in nitrogen. So we need to think here for a second. We have talked about low mass stars, and they start out with hydrogen, and then they make helium and carbon and oxygen. So where'd the nitrogen come from? Well, that's part of what happens in large mass stars, high mass stars. Um, the blue-white region is much lower speeds, still closer to the star, um, uh, includes a lot of dust. Eta Carinae is 4 million times the luminosity of our sun. So those are some of the things I want you to remember about this very large star. And so, where did the nitrogen come from? Hydrogen. Hydrogen and helium undergoing fusion, and then a helium fusing cell, a carbon and oxygen fusing cell, a magnesium neon oxygen fusing cell, silicon sulfur fusing iron in the core. So the nitrogen occurs from the reorganization of some of these molecules as it is expelled off the star. So when we have low mass stars, hydrogen, helium, carbon, and oxygen, and they're only big enough to get that much. Really massive stars, there is a lot more pressing down, so more pressure. More pressure means higher temperatures. Higher temperatures means that we can fuse all of these extra elements. So elements all the way up to iron are created in the core of high mass stars. When we get to iron in the core, and once the iron in the core gets big enough, then star dies, because it requires energy to fuse iron. Once there is a substantial amount of iron in the core, the star only has, minutes to live, and then it will explode in a supernova, which will be what we talk about next chapter.